Well, you guys, I guess Murphy's Law doesn't fail. I finished taping another maybe an hour and a half or something after this moment that you're watching right now. And when I went to review it at the end, it turns out that something happened. I kicked the camera and the thing got shifted and only half this, well not half, but 60% of the screen was visible. So I am hereby repeating everything that I did again. Hopefully at least one thing will be that it might be a little cleaner. That's the only thing, but boy, what a drag. So anyway, this is where I think it got, it connects with the previous one. I was writing down that the I about the rotated axis x, y prime would be x times y times the sine of phi minus theta multiplied times the cosine of phi minus theta dA divided by the sine of phi times the cosine of phi. Okay? And I had written here that the relationship sine of the difference between angles, sine of phi minus theta, is, to write it in, it's actually sine of phi cosine of theta minus cosine of phi sine of theta. And the other one, which is cosine of phi minus theta, is cosine of phi cosine of theta plus sine of phi sine of theta. Okay? All right. Now, in the previous presentation, I didn't do the multiplication, but I guess, I don't know, just in order to do something different here, entertain myself, let's just actually do this product, right? This times this. So we would have sine of phi cosine of theta minus cosine of phi sine of theta multiplied times cosine of phi cosine of theta plus sine of phi sine of theta, right? So doing that multiplication, we get, for this first term, cosine square of theta sine of phi cosine of phi, right? That took care of this one. Now this one is minus, let's see, what's repeated here? Cosine of phi squared times sine theta times sine theta times cosine theta, right? That was this one. Now this one, plus sine squared of phi sine theta cosine theta, and finally this one times this one looks like a minus, and what's repeated is the sine of theta. So sine of theta squared sine phi cosine phi, right? I'm going to go check just to make sure it doesn't happen again. That everything is in view. Yes, it is in view. Okay. So, so now we take this thing and we say cosine squared of theta minus sine square of theta, parentheses, is common factor of sine of phi times the cosine of phi, right? That took care of this and that. And now we have these two here, and we see sine theta, cosine theta. So that's plus sine of theta, cosine of theta, common factor of sine square of theta of phi minus cosine square of phi, right? So, okay, so that's that. Then we can, you saw the multiplication, right? So what I'm going to do now, this that's here is the product of these two things, right? So if I divide it by sine phi cosine phi, then we can see that this will go away, right? And this will be divided by sine of phi cosine of phi, correct? And therefore, I can take this to be that integral. Of course, there is the xy and the dA. So, okay, so I am going to erase here. And do it. This integral is this thing here, right? Now this part is a constant, right? That's cosine square minus sine square of theta. The integral is over the area and theta is constant. So we have cosine square of theta minus sine square of theta. And then we have the integral of xy dA, right? But the integral of xy dA is by definition Ixy, right? So we have, I've taken care of this part, xy times this, right? And then this is constant, goes out of the integral, and the integral of xy dA is just Ixy. And then we have the second part here, sine of theta cosine, that's constant. So sine theta cosine theta is outside. And then we have inside this integral, which is xy divided by sine phi cosine phi times sine squared of phi minus cosine squared of phi dA over the area. Okay? Fine. So, take all this stuff out. And then we have I x prime y prime equals cosine square of theta minus sine square of theta times Ixy plus sine of theta cosine theta. Now I want to deal with that integral over there. Now we have from before the fact that x is equal to d times the sine of phi and y is equal to d times the cosine of phi. You can go back and check on the drawing, right? That was part of the stuff that we did at the very original, and d is the distance from the point to the origin, right? So if we multiply x times y, we can see that x times y is just d squared sine of phi cosine of phi. Therefore, x times y divided by sine of phi cosine of phi is just d squared, right? So this part right here is just d squared. So we have the integral over the area of d squared parentheses sine squared of phi minus cosine square of phi dA. Okay? And that's the whole thing. Therefore, take all this off. Take all this off. Because we're almost there. Because then since we have that y is equal to d sine of phi, and x is equal to d cosine of phi, then we see that this part here is sine of theta cosine theta times the integral of d squared sine phi squared, that's the same thing as y squared dA, minus the integral, this is d squared cosine squared, so that's x squared, so that's x squared dA. Okay, and this is the same thing. So, by definition, the integral of y squared dA is what we call Ix. And by definition, the integral of x squared dA is what we call IY. Therefore, oh my god, I erased the first one. Well, it doesn't matter, I got it here. So we then conclude that Ix prime y prime is equal to this part here that I had erased, which is cosine square of theta minus sine square of theta times Ixy. And then this is just plus sine of theta cosine of theta times Ix minus Iy. Okay? That's it. So what that tells us then is that the product of inertia about any set of axes that is rotated by an angle theta, that is, you have some system, you have an x and y axis, and then you have a centroidal axis, and then you have some rotated axis x, y, y prime, which are rotated by an angle theta. It tells you simply that if you know the product of inertia about the xy, the product of inertia about the rotated axis is given by this, which depends on the angle, of course, depends on the Ixy about here, but also depends on what is Ix and Iy. All right? Fine. Now we can actually write it somewhat shorter than that, because we can use a relationship that says that cosine squared minus sine squared is cosine of 2 theta. So that kind of, writing a little bit less. And sine theta, cosine theta is the same as sine of 2 theta over 2. These are just well-known trigonometric relationships. And so we can also write it like this. Okay, which is a little bit shorter, and it's probably the expression that we tend to use in practice. Okay? So this is finally the one, right? That's what we use. Now, why did we do this? Let's remember. The point was that principal axes are the axes for which Ix prime y prime is 0, right? Therefore, in order to find what that angle is, we just simply make this equal to 0. So if we make it equal to 0, it's like making this equal to the negative of that. So I can just say that sine of 2 theta over 2 times Iy minus Ix, right? I changed the order, is equal to cosine of 2 theta times Ixy, right? From where, multiply by 2 on that side, divide this side by cosine of 2 theta, so you get something like tangent of 2 theta is equal to 2 Ixy divided by Iy minus Ix, and that's the formula, right? So, given Ixy, given Iy, and given Ix, you can calculate the tangent of 2 theta, and therefore the inverse tangent of 2 theta gives you 2 theta, and then divide by 2 gives you theta. Which means you find what is the rotation of the axis that gives you the principal axis. Needless to say, if Ixy is 0, then the tangent of 2 theta is 0. That means that 2 theta is 0, that means that theta is 0, you already have the right answer, the principal axis, right? Because Ixy was already 0. Okay? Now, let's put it in context like this. Let's say that what you had to do was to calculate, I don't know, let's say there's a section like this or something, right? And the centroid, let's say it's here, this is the x, this is the y-axis, right? X-axis, y-axis, you have some moment or something, you got to do some calculation. The point is, the first thing is, okay, you recognize this is a non-symmetrical cross-section and you need to know what the principal axes are, because otherwise you can't work. So you go in and you calculate your Ix, you calculate your Iy, and you calculate your Ixy. Now you might be doubting, how do I calculate the Ixy? You know the definition, but how do I actually do it? Well, it'll become obvious when we do the examples. But, the definition is product of x times y times dA, but let's say that we got it, right? About this axis. Now you plug it in here and you get a theta. So the theta now came out to be something, and you got like that, right? So this is the x prime, and this is the y prime. Okay, all set. So now you've got that. Now let's say that the problem said that, I don't know, let's say that the problem said that there was a moment about the x-axis, okay? Bear with me here, concentrate, okay? Let's say that it said that there was a moment about the x-axis. I don't know what would be easier for you if I use a number here or a theta. Let's say that, let me use a number. Let's say that this angle came out to be 23 degrees, okay, just for the sake of argument. So it turns out that these were the principal axis. I don't really mean that it was 23 in reality, because as you see, I'm just doing something generic here. But anyway, let's say that that's what you got. And let's say that what you had was that this beam had a moment about the x-axis that was, I don't know, 100, okay, in some units. Now to talk about what is that moment, let's say that that moment, if I call it plus, I mean that it was my thumb is pointing in the x-axis and the moment is like this. So that means that the moment is, with a double arrow, is like that. So let's say that that was the moment, 100. Okay, I'm not really going to do quantitative calculations. I'm doing numbers just to perhaps help you a little bit fix ideas. So you got this moment like that. Now, the problem is saying that it wants you to calculate the stress over here. It says, what is sigma there? That's what the problem wants to know. And you know that your formulas, that is my over I, they only work because here we only have one material, so we don't have to go through the moment to curvature, curvature to strain, strain to stress. We can just simply say it's my over I. Okay? So I recognize that this is the situation I got, and I want to get the stress there. And I know that I have to use my my over I only, but my moment is not about the principal axis, right? So I got to get it into the components that are about the principal axis. So I go like this, right? And I see that there's a moment here. Let's say we call it A. And then there is this other component here, right? And say we call it B. Fine? This being 90 degrees. And this is 23. So we can see what? That A is 100 times the cosine of 23, right? And B is 100 times the sine of 23. Okay, so now we know the moments about the principal axis. Cool. So now that we know the moments about the principal axis, and I want to get the stress there, I know my formula is my over I, and I'm just going to do it one at a time. I don't think about two things, I think about one thing at a time. So I'm just saying, what if I only had A? So if I only had A, my moment would be like this, my distance would be this, right? Because this is the axis. So that would be my distance. And I'm going to call that distance N1. Some things I'm going to use symbols, sometimes numbers. Whatever I think it's going to be cleaner. So that's N1. So I can say the sigma, if I only had A, would be what? Would be A, which is the moment. The distance for that kind of a moment is N1. And the moment of inertia is the moment of inertia about x prime, right? Now, which sign would that stress have? Tension or compression? Well, if I was in class and from my prior experience of many years, I'd say some people would say tension, some people would say compression. After a little while, there would tend to be some sort of consensus, and the consensus is usually correct. And that would mean, in this case, that is tension, right? Because this moment, with the arrow at A, you see my thumb pointing that way, the hand tense like this. That means that the stresses that are above the axis are coming out and below are coming in. So it's like this. So coming out means these are tensile stresses above the axis, right? So that point is above the axis, so we got tension there. So if I use plus, I'm going to say that's tension, right? And it's a plus. And so that's fine. Now, if I only had B, let me say tension. If I only had B, then B is going to be like this, right? So that means that the stresses on the right side of the Y prime are coming up, and the ones on the left side or the bottom side are coming down. So it's, turning like this. So there is going to be what due to B? Also tension there, right? Coming out and coming in here. This one is like this, coming out and coming in here. So I also have tension. And what would that be? Well, it would be sigma equals B, which is that moment. And what is the distance? Well, it's bending about this axis right now. So the distance would be this one. We can call that N2. And so it's B times N2. And then what else? The moment of inertia about Y prime. And then since that's tension, in this case I don't have to subtract that, so the total stress, which is the answer, would be this plus this. So if I call this 1 and 2, then it's just 1 and 2, right? And it's tension. Okay, so that would be the end of the problem. Now, let's look at it. What is it that you would need to calculate? Well, you would need to calculate how far is this. So that's one thing, right? Now that's a geometry problem. It's like how far is it from a line to a point? Depending on how good your trig is and how good you can draw things big enough and so on, you might be able to do it quickly. Sometimes it may be confusing. But the point is that that's a geometry. If you drew it to scale, you could almost measure it. And you have to measure M2, which is this distance, right? From the axis to that point, the perpendicular distance. So that's fine, those are two geometric things. But also, you'd have to calculate the moment of inertia about the X prime and Y prime. Now, that's kind of cumbersome, right? Because to go and calculate the moment of inertia about these two things, I mean, in principle, I guess you could do it, but it's really a pain in the neck to have to do that. So we don't go back to 0 and start calculating Ix prime and Iy prime, because it turns out that it can be shown that once you have Ix, Iy, and Ixy, you can calculate the inertia about any rotated axis easily from a formula that can be derived following essentially the same ideas that I was doing for you here, but that I will skip in this aspect, and I will just give you the formula. And the formula is that once you know the moment of inertia about some axis, then the moment of inertia about any other rotated axis